Tonight, we're going to explore something that appears simple on the surface, yet is actually one of the most mind bending ideas in all of science: the light year. You've heard this term countless times. It's used in documentaries, in astronomy videos, in every conversation about distant stars and galaxies. But here's the surprising truth: most people have never really stopped to understand what a light year means. And when you finally do, when you grasp the scale hidden inside that single unit of distance, it changes the way you look at the universe forever. A light year isn't just a measurement, it isn't just a very big number. It is a stretch of space so enormous, so far beyond everyday experience, that our minds struggle to hold it. By the end of this journey, you'll understand why astronomers rely on this extraordinary unit, and why the usual measurements, kilometers, miles, collapse under the weight of cosmic distances. Before we dive deeper, if you enjoy exploring concepts like this, a small like or subscribe truly helps the channel grow. It's a simple gesture for you, but it makes a tremendous difference for me. Now let's begin. We'll start with something familiar: the distances of everyday life. You already understand distance intuitively. You know the walk to the grocery store. You know the route to your workplace, the drive to the next town, the hours it takes to visit friends or family. These distances fit inside your world. They're anchored to time, to personal memory, to physical effort. A kilometer is something your body understands. It's about 10 to 12 minutes of walking, a distance you've covered hundreds, maybe thousands of times. So when someone says the store is 5 kilometers away, you can imagine the drive. You know the stoplights, the landmarks, the rhythm of the trip. When someone says a city is 200 kilometers away, you mentally prepare a couple of hours of driving, maybe fuel up the car, maybe plan a rest break. These numbers are human scaled. They align with the limits of our biology, our perception, and our daily experience. But push these measurements further, and they begin to strain. Take the distance from New York to Los Angeles, around 4,500 kilometers. It's a long flight, yet you can still picture it. Millions of people make that trip every year. You can imagine the changing landscape: dense urban coasts, sprawling plains, rising mountain ranges, desert, then finally the Pacific shore. Large, yes, but not unimaginable. Even the Earth itself, vast as it feels, remains within conceptual reach. Its circumference at the equator is about 40 to 75 kilometers. A huge number, but explorers have circled the globe. Planes do it now in under 2 days. The Earth is big, but not beyond grasp. But then we step outward beyond the boundaries of our world. The distance from Earth to the Moon is about 384,000 kilometers. And here, something happens. Our human sense of scale breaks. 384,000 kilometers is no longer a journey you can visualize. You can't imagine driving it. You can't imagine walking it in a lifetime. For the first time, the numbers float free of intuition. They become abstract. This is the moment when our familiar units, kilometers, miles, stop being useful. The universe is simply too large, too empty, too stretched out for them to make sense anymore. And that is exactly why the light year exists. That distance, 384,000 kilometers, is already beyond anything we can visualize in a meaningful way. It isn't like driving across the country. It isn't like sailing around the world. It belongs to an entirely different category of scale. There is no road that stretches toward the moon, no comforting landmarks along the path, no rest stops where you can pause and gather yourself. It is simply distance, pure, unbroken distance across an expanse of empty space. So, how would you even begin to travel that far? The Apollo astronauts made that journey in about 3 days. To do it, they rode on rockets powerful enough to accelerate them to speeds near 11 kilometers per second, around 39,600 kilometers per hour. Let that sink in for a moment. That is roughly 400 times faster than highway driving, 400 times faster than anything your everyday experience can prepare you for. And even at that astonishing velocity, a speed that required some of the most advanced engineering, the largest fuel tanks, and the most intense thrust ever produced at the time, it still took 3 full days. 3 days of gliding through a silent void at speeds no human had experienced before, just to reach Earth's nearest celestial neighbor. And remember, that's just the moon, the closest world to Earth, a place so near that you can spot it, with the naked eye trace its craters with a small telescope, and watch its phases glide across the sky every month. It feels close, almost familiar, yet reaching it requires days of travel at unimaginable speed. When we start talking about distances beyond the moon, to the planets, to the sun, to the nearest stars, kilometers simply stop working. The numbers grow so huge, they lose all emotional weight. They become symbols rather than sensations, strings of digits that don't connect to anything in your lived experience. Your brain cannot but attach meaning to them. Take the distance from Earth to the Sun, around 150 million kilometers. Try for just a moment to picture that. You can't. No one can. Your mind registers it as big, but not big in a way you can feel. Nothing in your daily life involves distances remotely close to that scale. Nothing in all of human history required our brains to evolve the ability to imagine such immense space. We learned to understand the distance to the next river, the next shelter, the hunting grounds we could reach before nightfall. We never needed to, and never could evolve an intuition for 150 million kilometers. Even the mighty Apollo spacecraft, those machines that carried humans to the moon, would be almost painfully slow on the scale of the solar system. Traveling at 11 kilometers per second, it would take them about 160 days, more than 5 months, just to reach the distance of the sun. And that's assuming they traveled in a perfectly straight line, which spacecraft never do. Suddenly, our familiar units, kilometers, hours, days, feel tiny, fragile, utterly overwhelmed by the immensity of space. This is the moment when astronomy needs a new language, a new unit, something capable of expressing distances so enormous that ordinary numbers collapse beneath them. And that is why the light year exists. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds up to 192 kilometers when it's close to the sun, using its gravity to slingshot itself to higher and higher velocities. Even at this incredible speed, about 17 times faster than the Apollo spacecraft, The probe still takes months to complete a single orbit around the sun. And remember, the sun is close. It's right here in our cosmic neighborhood. It's the star we orbit, the source of all the light and heat that makes life on Earth possible. We see it every day. It feels familiar, and yet it's still 150 million kilometers away, a distance so vast that even our fastest spacecraft needs months to traverse it. But when we start talking about the distances to other stars, even the sun's enormous distance becomes tiny by comparison. The sun is our nearest star at 150 million kilometers, but the next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes months to cross with our fastest technology. This is why astronomers needed a different unit of measurement. Not to complicate anything, not to overwhelm people with giant numbers, but because kilometers simply stop working when applied to cosmic distances. Using kilometers to measure the distance to stars would be like using millimeters to measure the distance between countries, technically possible, but completely impractical. The numbers become so large, they lose all meaning. They stop being distances and instead become abstract mathematical symbols disconnected from human experience. So astronomers came up with something different, the light year. And here's what you need to understand right from the start: a light year is not a measure of time. Even though the word year is in the name, a light year is purely a measure of distance, the distance that light travels in 1 year. Why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster, not because we lack the technology, but because the speed of light is woven into the fundamental laws of physics. It is constant, unchanging everywhere in the universe. Whether you're on Earth, on Mars, drifting in another galaxy, or standing near the edge of the observable universe, light always travels at the same speed, about 300,000 kilometers per second. Let me say that again, because it's important: 300,000 kilometers every single second. Light travels 300,000 kilometers in the time it takes you to blink, breathe, or even notice that a moment has passed. This isn't an approximation or a rough estimate. It's been measured with extraordinary precision. The exact value is 299,792, 458 kilometers. But for our purposes, rounding to 300,000 is close enough. That is incredibly fast, almost unimaginably fast. To put it in perspective, light could travel around Earth's equator roughly 7.5 times in a single second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. Nothing in our everyday experience comes remotely close to this speed. The fastest thing most people ever encounter is an airplane cruising at around 900 kilometers per hour, or roughly 0.25 kilometers. Light travels more than 1 million times faster than that. Even the fastest car ever built, the thrust SSC, reached about 200 kilometers, or around 0.33 kilometers. Compared to that, light is about 900,000 times faster. And even the Parker Solar Probe, the fastest spacecraft humanity has ever created, reaching 192 kilometers at its peak, still moves at only 0.064% the speed of light. By human standards, it's unbelievably fast, but compared to light, it's crawling. When you flip a switch in a dark room, the light reaches your eyes essentially instantly, not because the bulb is magical, but because the room is small. The light travels from the bulb to your eyes in about 10 billionths of a second, so fast that your brain cannot perceive any delay. As far as you're concerned, the illumination appears immediately. But the light did travel. It took time, just not enough time for you to notice it. And this leads to one of the most fascinating aspects of light travel. When you look at anything in the universe, you're not seeing it as it is, you're seeing it as it was. When you look at the sun, you're seeing it 8 minutes and 20 seconds in the past because that's how long its light takes to reach Earth. The sun is so far away that even traveling at 300,000 kilometers light needs more than 8 minutes to cross the space between us. This has a strange implication. If something happened on the sun right now, if it suddenly dimmed, flared, or even exploded, we wouldn't know for more than 8 minutes. The event would occur, but the light carrying that information would still be on its way. We would continue to see the sun exactly as it was, not as it is, until those 8 minutes had passed. When you look at the moon, you're seeing it as it was 1.3 seconds ago. Not much of a delay, but still a delay. When astronauts walked on the moon and spoke to mission control, every word took 1.3 seconds to reach Earth, and every reply took another 1.3 seconds to travel back. Every conversation had almost a 3-second gap between each exchange. You can clearly hear this delay in the old recordings. There's always this pause, this subtle lag, because the radio signals carrying their voices traveled at the speed of light. And even light fast as it is, still needs time to cross the distance between Earth and the moon. Light doesn't move instantly. It has a speed, and that speed, although unimaginably fast by human standards, is still finite. This simple fact is one of the most important discoveries in the entire history of physics. Before the late 1600s, almost everyone assumed that light traveled instantaneously. You opened your eyes and the world appeared. You lit a candle and the room was immediately illuminated. There was no visible delay, no moment of waiting, so the natural conclusion was that light must move infinitely fast. But in 1676, a Danish astronomer named Ole Romer made an observation that changed everything. He was studying the motions of Jupiter's moons, particularly Io, and he noticed something odd. The times when Io disappeared behind Jupiter didn't match the predictions. When Earth was closer to Jupiter in its orbit, the eclipses happened earlier than expected. When Earth was farther away, they happened later. Rummer realized that the only explanation was that light took time to travel the changing distance between Jupiter and Earth. When we were farther away, the light had a longer journey to complete, and so events appeared delayed. He calculated that it took light about 22 minutes to cross the diameter of Earth's orbit. His number wasn't perfect. He didn't have precise measurements of Earth's orbit, but his conclusion was revolutionary. He proved for the first time in history that light has a finite speed. Today, we know the speed of light with extraordinary accuracy. We've measured it using lasers, atomic clocks, interferometers, and the most sophisticated instruments humans have ever built. We've confirmed that this speed is constant. It doesn't change based on your motion, your location, or your frame of reference. And we've discovered that this constant isn't just the speed at which light happens to travel, it is a fundamental property of space time itself. So when we say a light year, what we really mean is the distance that light travels in 1 year at this unchanging cosmic speed. Let's calculate it. Light travels at 300,000 kilometers. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of that together, 300,000 to 60, 24, that says 365, we get about 9.46 trillion kilometers. To be exact, the number is 9, 460, 730, 472, 58, or point 0.8 kilometers. But for simplicity, astronomers usually just say 9.46 trillion kilometers. That's what a light year is, not a measure of time, despite the misleading name, but a measure of distance, the staggering distance that light, the fastest thing in the universe, travels in a single year. And that is the number we're going to try to make sense of tonight. Because in understanding what a light year truly means is essential to understanding our place in the universe, the gaps between stars, and the true scale of the cosmos. But before we can grasp distances measured in trillions, we need to talk about what a trillion actually is, because most people have no intuitive sense of how large that number really is. We casually mention millions, billions, and trillions in everyday conversation, but very few of us ever stop to consider the scale they represent. We hear about government budgets measured in the trillions, about billionaires with unfathomable wealth, about millions of people living in a city or moving across a continent, but we rarely grasp the enormous differences between these numbers. They all sound large, so our brains tend to group them together as big, but they're not even close. The differences between them are staggering. A million is 1,000 thousands. If you saved just $1 every day without ever missing a day, you would reach $1 million in about 740 years. That's a long time, but it's at least imaginable. You can picture human history stretching back 740 years to ancient Greece, to early Rome, to a world where people were already building cities, writing books, debating philosophy, creating the foundations of Western civilization. It's a vast time span, but one we can mentally place on the historical timeline. A billion is 1,000 millions. Now the scale jumps dramatically. If you saved $1 every second, not every day, but every single second, it would still take you about 32 years to save $1 billion. That's more than the time it takes an entire generation to grow up. If you started counting seconds at the moment of your birth and never stopped, not for sleep, not for meals, not for a breath, you would be 32 years old by the time you reached 1 billion. Think about that difference. A million seconds is roughly 11 and a half days. A billion seconds is 32 years. The jump from a million to a billion is enormous, far bigger than most people realize. Now consider a trillion. A trillion is 1,000 billions, and it's here that numbers begin to detach completely from anything we can intuitively relate to. If you counted to a trillion, saying one number every second without ever stopping, it would take you about 31,700 years. To put that in perspective, 31,700 years is longer than all of recorded human history. Agriculture, the foundation of civilization, was invented only about 10,000 years ago. Before that, every human on Earth lived as a hunter gatherer, traveling in small bands, following herds and seasons. Writing systems didn't appear until about 5,000 years ago in Mesopotamia. The pyramids were built around 4,600 years ago. The wheel likely appeared about 500 years ago. To reach a trillion seconds, you would have needed to start counting long before any of that existed. Before the first farm, before the first city, before the first written word. You would have had to begin counting when humans still lived in small tribal groups using stone tools, making simple shelters, leaving fleeting traces in cave paintings. You would have kept counting through the rise and fall of every empire, through every war and every moment of peace, through every invention, from bronze to steam engines to computers, through the entire story of humanity, and you would still have thousands of years left to go before reaching 1 trillion. Let's make it even more concrete. Around 31,700 years ago, Earth was in the last ice age. Humans hunted woolly mammoths and giant ground sloths. They shaped sharp stones into tools. They migrated slowly across Europe and Asia. Modern humans had only recently spread out of Africa. There was no written language, no agriculture, no metal, no cities, just survival and simple tools. That is how far back a trillion seconds takes you, and a light year is 9.46 trillion kilometers. Every single one of those kilometers is a real physical kilometer, the same kilometer you could walk in 10 to 12 minutes at a normal pace. And there are 9.46 trillion of them, each one a separate, distinct kilometer long segment, each one the length of a casual walk to a nearby store. So when we say a light year is 9.46 trillion kilometers, we are talking about a distance that dwarfs anything in our everyday experience, a distance that is real, measurable, calculable, but far beyond the scale our brains evolved to handle. You can write it down, you can calculate with it, you can put it into equations, but truly understanding it, that's something else entirely. But grasping that distance intuitively is nearly impossible. Our brains simply didn't evolve to handle numbers this large. We evolved to count the number of people in our tribe, the number of animals in a herd, the number of days until the seasons changed. We're good at small numbers, at things we can see, touch, and track. We can count to a few hundred without effort, maybe a few thousand if we really focus. But 9.46 trillion. That number is so far beyond our cognitive limits that it might as well be infinity. Our intuition breaks long before we get anywhere close to understanding it. So, the best way to understand a light year is to build up to it, gradually starting with distances we can comprehend and scaling upward step by step. We're going to take this journey slowly, moving from the familiar to the unfamiliar, watching how distances that once felt enormous begin to look tiny compared to what comes next. Let's start with something small, one light. Second, the distance light travels in a single second, 300,000 kilometers. That's about the distance from Earth to the Moon and 3/4 of the way back. Think about that for a moment. Light leaves Earth, travels all the way to the Moon, 384,000 kilometers away, bounces back, and gets most of the way back home again. And all of that happens in 1 second. One single heartbeat. During the Apollo missions, astronauts talking to Mission Control in Houston experienced a communication delay of about 1.3 seconds each way. The astronauts would say something, and Mission Control wouldn't hear it until 1.3 seconds later because the radio signal traveling at the speed of light needed that long to cross the gap. When Mission Control replied that signal needed another 1.3 seconds to reach the moon. So every exchange had a nearly 3-second delay built into it. It's subtle when you listen to the recordings, but once you notice it, it's always there. A tiny pause created by nothing more than distance and the unbreakable speed limit of light. Now scale up 1 light minute. 1 light minute is 60 light seconds or about 18 million kilometers. The sun is about 8 light minutes away from Earth, roughly 150 million kilometers. So a single light minute is only around 12% of the Earth Sun distance. If you could somehow stand on the sun, not that you could, because it's a roiling sphere of plasma with a surface temperature of about 500 degrees Celsius. But if you could, and you waved your hand, but if you could somehow stand there and look toward Earth, you'd be seeing our planet as it was 8 minutes and 20 seconds ago. If Earth suddenly exploded, you wouldn't know for over 8 minutes. The event would occur instantly, but the light carrying the information about that event would still be making its way across space. Until that light arrived, Earth would appear perfectly normal. This delay isn't just a thought experiment, it has real practical implications for space exploration that most people never consider. When NASA operates rovers on Mars, there is always a communication delay because Mars is so far away. At its closest, when Earth and Mars are on the same side of the Sun, the distance between them is about 32 million kilometers, roughly 2 light minutes. At their farthest, when the planets sit on opposite sides of the Sun, the distance stretches to about 400 million kilometers, or roughly 22 light minutes. This means that when the Perseverance rover is working on the Martian surface, every command sent from Earth takes between 2 and 22 minutes to arrive depending on where Mars is in its orbit. And any data the rover sends back takes just as long to return. You cannot drive a rover on Mars in real time like a remote controlled car on Earth. The delay is simply too long. Instead, NASA engineers have to plan each day's activities extremely carefully. They examine images and data from the previous day, choose a route, write a detailed sequence of commands, transmit those commands to Mars, and then wait. If something goes wrong, if the rover gets stuck, slips, or encounters an unexpected obstacle, they can't react immediately. They must wait for the rover's report to reach Earth, which takes anywhere from 2 to 22 minutes. Only then can they analyze the problem, devise a solution, send new commands, and then wait again for those instructions to travel back to Mars. A problem that would take seconds to solve on Earth can easily take an hour or more on Mars. Now scale up again. 1 light hour is 60 light minutes, about 180,000 kilometers, over a billion kilometers. A distance so large that even imagining it stretches the limits of our intuition. The planet Saturn, at its closest approach to Earth, is around 1.2 light hours away. Saturn is one of the farthest planets visible to the naked eye, a magnificent ringed world, known since ancient times, and yet it sits more than an hour of light travel away from us. When the Cassini spacecraft orbited Saturn from 2004 to 2017, capturing some of the most breathtaking images ever taken of the planet and its moons, there was always more than an hour-long delay between the moment Cassini took a photograph and the moment that photograph reached Earth. The spacecraft would snap a picture, convert it into digital data, transmit that data as a radio signal, traveling at the speed of light, and over an hour later, scientists on Earth would finally receive it. Because of this delay, Cassini couldn't be controlled in real time. Engineers couldn't watch its camera feed and steer it through Saturn's rings like piloting a drone. Instead, they had to program long sequences of commands days or even weeks in advance, upload them to the spacecraft, and trust Cassini to execute its instructions correctly without immediate supervision. It was exploration done with patience, precision, and faith in the spacecraft millions of kilometers away. If something went wrong out there, the spacecraft had to be smart enough to handle it autonomously, to recognize the problem and switch itself into a safe mode. Because by the time the issue was detected, reported back to Earth, analyzed, and new commands were sent, more than 2 hours would have passed. In that amount of time, the situation on board could have changed completely. You cannot depend on real time control when every interaction is separated by hours of silence. Now let's scale up again. 1 light day is 24 light hours, about 25.9 billion kilometers. At this point, the distances we're describing are so immense that even our fastest spacecraft become unimaginably slow in comparison. Voyager 1 launched in 1977 and still transmitting faint signals back to Earth is the most distant human-made object in existence. As of 2025, it sits roughly 24 light hours away from us. Think about that. Nearly 50 years of uninterrupted travel at a speed of about 17 kilometers per second, around 200 kilometers per hour. Yet it still hasn't reached even a single light day from Earth. At 17 kilometers, you could cross the entire United States in about 2 minutes. It is impossibly fast, by human standards, faster than anything we experience on Earth. But compared to the speed of light and the size of the cosmos, it's barely moving. The distance Voyager has reached is roughly the distance to the heliopause, the boundary where the sun's influence finally fades and interstellar space truly begins. The heliopause is the point where the solar wind, a constant stream of charged particles flowing outward from the sun, slows, weakens, and merges with the interstellar medium, the thin gas and dust that fill the space between stars. Voyager 1 crossed this boundary in 2012, becoming the first human made object to enter interstellar space. It was a monumental moment for humanity, a milestone in our attempt to reach beyond our home star's influence. And yet, despite this achievement, Voyager is still within one light day of the Sun. In cosmic terms, it's still in our front yard. Next, consider 1 light week, 7 light days, about 181 billion kilometers. This is a region of space where no human made craft has ever been and none will be for many decades, possibly centuries. This is deep space, far beyond the planets, far beyond anything we have touched, visited, or directly explored. At 1 light week from the sun itself would no longer dominate the sky. Instead of the overwhelming disk of blinding brightness we see from Earth, it would appear simply as a very bright star, brighter than the others. Yes, but still just at a point of light in a vast darkness filled with thousands of stars. Floating out here a week of light travel from home, you would finally see the sun the way it would appear from another star system, unmistakable, but not exceptional. A light month is roughly 30 light days, about 778 billion kilometers. At this distance, the sun is still visible, still brighter than the nearby stars, but no longer the unmistakable center of a planetary system the way we perceive it from Earth. Out here, the structure of our solar system begins to dissolve into the surrounding galaxy. At this distance, if you looked back at the sun through a telescope, you'd see it as just another star, bright, but not overwhelmingly so, not the dominant presence we're used to. It would no longer flood your sky with light. The entire solar system, with all its planets, moons, asteroids, and comets, would be reduced to a compact and barely noticeable cluster of faint points. Even with a powerful telescope, you might pick out Jupiter as a tiny dot, but the inner planets would be completely washed out by the sun's remaining glare. Everything we think of as the solar system, every world we've explored, every planet we've mapped, every destination we've sent spacecraft to, would be squeezed into a minuscule region surrounding an otherwise ordinary looking star. And now we reach the next step, 1 light year. 1 light year is 365 light days. It's 12 light months. It's 52 light weeks. It's 760 light hours. It's 525, 600 light minutes. It's 31,536,000 light seconds. See how quickly these numbers explode in scale. We started with 1 light second, already an immense distance, by human standards, roughly the distance from Earth to the Moon, and more than halfway back. And then we kept multiplying 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And only now are we arriving at 1 light year. 946 trillion kilometers. That's the distance light travels in a single year, moving at 300,000 kilometers every second for 365 days without pause. This is the fundamental unit astronomers use to measure the distances between stars, because stars are spaced apart at scales where only light years make sense. Kilometers become useless. Even millions and billions become unwieldy. Light years bring clarity to an incomprehensibly large universe. So, why do astronomers use light years? Because every other option is worse. Imagine if astronomers insisted on using kilometers for everything. Proxima Centauri, the nearest star to the Sun, is about 40 trillion 140 billion kilometers away. That number is awkward, impossible to remember, and gives you no intuitive sense of scale. But if I tell you Proxima Centauri is 4.24 light years away, the information becomes clean, meaningful, comparable. If one star is 4 light years away and another is 40 light years away, you instantly understand that the second is 10 times farther. Light years give us an intuitive handle, not perfect, but far better than wrestling with strings of digits dozens of characters long. Light years also connect distance and time in a surprisingly useful way. When you look at a star 4 light years away, you are seeing light that left that star 4 years ago. You're literally looking into the past. This becomes essential when studying the universe because the deeper we look, the further back in time we see. And this connection exists because the speed of light is not just fast, it is the speed limit of the universe. Nothing can travel faster. Not because we lack advanced technology, not because our rockets aren't powerful enough, but because the laws of physics themselves forbid it. The speed of light is woven into the structure of space-time. It defines how space-time energy and matter interact. Einstein's theory of special relativity, published in 1905, showed that as objects approach the speed of light, strange things happen. Effects that seem impossible in everyday life begin to dominate motion at extreme velocities. And these aren't just theoretical predictions, they're observed facts confirmed by countless experiments over the past century. Time really does slow down for an object in motion relative to someone who is stationary. This effect is called time dilation, and it has been measured directly. The object's mass, more precisely, its inertia increases as its speed increases. It becomes harder and harder to accelerate. The amount of energy required to push it faster rises without limit as you approach the speed of light. To reach the speed of light would require infinite energy. And because the universe does not contain infinite energy, nothing with mass can ever reach light speed. Let me explain why this happens. In everyday life, if you're on a train moving at 50 km/h and you throw a ball forward at 20 km/h relative to the train, someone standing beside the tracks would see the ball moving at 70 km/h. The speeds simply add. This feels natural, and it works perfectly well for normal speeds. But Einstein showed that this simple addition breaks down completely at speeds close to the speed of light. If you're on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might expect the light to travel at 1.5 times the speed of light, at least from the perspective of someone watching you fly past. But that's not what happens. The light still travels at exactly the speed of light, 300,000 kilometers from your perspective and from the perspective of the outside observer. Both of you measure the same value. This seems impossible. How can two observers moving relative to each other at enormous speeds both measure the same speed for the same beam of light? The answer is that space and time themselves adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the viewpoint of a stationary observer, and lengths in the direction you are moving actually contract. Distances shrink, time stretches. These are not illusions, these are physical effects built into the structure of the universe. Time and space are not absolute, they're relative. They depend on your motion. The only thing that is absolute, the one quantity that never changes for anyone anywhere, is the speed of light. And this isn't speculation. It's been tested and confirmed repeatedly. Particles accelerated to near light speed in particle accelerators survive far longer than identical particles at rest. The faster they move, the slower time flows for them when relative to us. Their lifetimes stretch out in ways that would be impossible without time dilation. This isn't theory, it's measured fact. Even GPS satellites orbiting Earth experience time dilation. They move fast enough and are far enough from Earth's gravity that time flows at a slightly different rate compared to clocks on the ground. Engineers must correct for these relativistic time shifts. If they didn't, GPS would drift out of alignment by several kilometers within hours. The fact that GPS works at all is direct everyday proof that time dilation is real. Cosmic rays, high energy particles that strike Earth's atmosphere, create particles called muons high in the sky. Muons decay extremely quickly. They live for only millionths of a second. Under normal circumstances, they shouldn't survive long enough to reach the ground. Muons are subatomic particles that decay extremely quickly with a half-life of about 2 microseconds. At that rate, even traveling near the speed of light, muons created high in Earth's upper atmosphere shouldn't have enough time to reach the ground before disintegrating. And yet we detect muons at ground level all the time. Why? Because from our perspective, the muons are moving so fast that time dilation dramatically extends their lifetimes. What is only 2 microseconds in the muon's own frame of reference becomes much longer from hours long enough for them to survive the journey through the atmosphere and reach Earth's surface. Time itself stretches for them because of their extreme speed. Only massless particles, like photons, particles of light, can travel at the speed of light. Photons have no rest mass, so they don't require infinite energy to reach light speed. In fact, photons must always travel at light speed. They cannot slow down or speed up. From the moment they are created to the moment they are absorbed, they move at exactly 300,000 kiloseconds. No faster, no slower. That is simply their nature. This has profound implications for space travel that go far beyond mere engineering challenges. Even if we developed perfect propulsion systems, even if we had unlimited energy, even if we solved every technological problem imaginable, we still could never exceed the speed of light. The 4.24 light years to Proxima Centauri represents an absolute minimum travel time of 4.24 years, even in the most optimistic scenario where a spacecraft somehow reaches a velocity arbitrarily close to the speed of light. And that's just to the nearest star. Most destinations in the universe are vastly, vastly farther away. Science fiction often proposes ways around this cosmic speed limit. Warp drives that bend space around a spacecraft, allowing it to effectively move faster than light without actually breaking the speed of light relative to the space it travels through. Wormholes that create shortcuts through space-time, connecting distant regions of the universe. Hyperspace, an alternate dimension where the laws of physics operate differently, enabling faster than light travel. These ideas are imaginative, and a few, like warp drives, have the slightest glimmer of theoretical grounding. The Alcubierre drive, proposed in 1994, is a mathematical solution to Einstein's field equations. In theory, it could allow faster than light travel by contracting space in front of a spacecraft and expanding space behind it, effectively moving the ship without the ship itself needing to exceed light speed. But there are problems, huge ones. The Alcubierre drive would require exotic matter with negative energy density, a form of matter that has never been observed, may not exist, and may even be impossible according to the laws of physics. And even if such matter did exist, the amount required might exceed the total mass energy of the entire observable universe. There's also the issue of causality. Faster than light travel implies the possibility of traveling backward in time, creating paradoxes that break fundamental logic situations where cause and effect no longer make sense. Wormholes, if they exist at all, would likely be incredibly unstable. They might wink into existence at the quantum scale for tiny fractions of a second and collapse long before anything could pass through them. Keeping a wormhole open long enough for travel might require energy greater than the energy content of the universe, and again raises causality paradoxes similar to those in warp drive scenarios. As for hyperspace, it is pure speculation, a storytelling device with no support in known physics, no mathematical framework, no experimental evidence. It's fun, it's imaginative, but it's fiction. There's no evidence that any such shortcut, warp drives, wormholes, hyperspace exists or could exist. As far as we know, based on more than a century of careful experiments and precise observations, the speed of light is an absolute barrier. It isn't a technological challenge waiting for a breakthrough. It isn't an engineering problem we might one day solve. It is a fundamental property of the universe. So when we talk about stars that are hundreds or thousands of light years away, we're talking about distances that may be permanently unreachable by any technology that obeys the laws of physics as we currently understand them. A light year doesn't just measure distance, it also measures a boundary, a limit built into the fabric of reality. Beyond this boundary, even the concepts of cause and effect begin to stretch and distort. To understand this scale in practical terms, let's talk about Proxima Centauri, our closest stellar neighbor. Understanding Proxima Centauri gives us a tangible sense of what it means to say that even nearby stars are unimaginably far away. Proxima Centauri is a small red dwarf star in the Alpha Centauri system, a triple star system located just beyond our own. Two of those stars, Alpha Centauri A and Alpha Centauri B, are sun-like stars orbiting each other. They're similar in size and brightness to our sun and they revolve around their common center of mass every 79.9 years, locked in a slow gravitational waltz that has been unfolding for billions of years. If you could see them up close, Alpha Centauri A and B would appear like twin suns circling each other against a backdrop of black interstellar space, a breathtaking double sunset stretching across alien horizons. Proxima Centauri is much smaller, about 1/8 the sun's mass and roughly 1/17 its diameter. It's so faint that you can't see it with the naked eye. Even though it's the closest star to us beyond the sun, a telescope is required to spot it at all. Red dwarfs like Proxima are actually the most common type of star in the Milky Way, making up around 70% of all stars. Yet none of them are visible without a telescope simply because they're so dim. Every star you can see with your naked eye is either significantly larger and brighter than our sun, or it isn't a star at all, but a planet reflecting sunlight. Proxima Centauri sits 4.24 light years away, about 40,140,000,000,000 kilometers. That's a 40 followed by 12 zeros. To put this into perspective, imagine traveling at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reaches speeds up to 182 kilometers when it slingshots close to the sun. Even at that extraordinary speed, it would take you about 600 to 800 years to reach Proxima Centauri. 6,800 years, more than the entire span of recorded human civilization, longer than the time since the pyramids were built, longer than the time since the last ice age ended. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have begun your journey at the exact moment humans first carved symbols into clay tablets, traveled continuously at the fastest speed any human spacecraft has ever reached, and you would still be traveling today, still thousands of years away from your destination. Because of this, scientists and engineers have proposed concepts for much faster spacecraft. One of the most ambitious is the Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. The idea is to use incredibly powerful ground based lasers to accelerate tiny spacecraft to about 20% of the speed of light. The concept is elegant and scientifically sound, at least in principle. You build a spacecraft that is essentially a computer chip with a camera weighing perhaps a gram attached to an ultra thin reflective light sail made of material only a few atoms thick. Then from Earth, you fire massive arrays of lasers at the sail. The photons push on it, and because the craft is unbelievably lightweight, it can be accelerated to extraordinary speeds. At 20% of light speed, roughly 60,000 kilometers, a probe could travel to Proxima Centauri in about 20 years. Add another 4 years for the signals to travel back to Earth at light speed, and you could potentially receive data from Proxima Centauri 24 years after launch. That's within a single human lifetime. You could launch the mission when you're young and live long enough to see the results. That possibility alone is breathtaking. But the engineering challenges are enormous, perhaps insurmountable for current or near future technology. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total output of about 100 gigawatts, roughly the power of 100 nuclear reactors, all focused into a precisely controlled beam a few kilometers wide. This beam would have to track the tiny spacecraft perfectly as it accelerates. If the beam drifts even slightly, the sail could slip out of alignment, cutting off acceleration and leaving the probe coasting at whatever speed it had reached. Second, the spacecraft must survive the journey. At 20% of the speed of light, collisions with even microscopic particles become catastrophic. A speck of dust smaller than a grain of sand striking the probe at that speed would release the energy of a large bomb. The spacecraft needs shielding, but any shielding adds weight. And weight is the enemy when you're relying on light pressure for acceleration. Every additional gram requires exponentially more laser power. Third, communication becomes a monumental challenge. The spacecraft must send data back across 4.24 light years. A tiny gram scale probe would need a laser or radio transmitter strong enough to deliver a detectable signal to Earth from unimaginable distances. At that range, signals spread out enormously. The power needed to send even a few bits of information becomes substantial, and you must fit this capability into a spacecraft the size of a microchip. It's the communication equivalent of shouting across an ocean and expecting to be heard clearly on the far shore. Fourth, you need to actually hit the Proxima Centauri star system, passing through it at exactly the right distance and angle to gather meaningful data. At 20% the speed of light, the spacecraft is moving so fast that it crosses the orbit of Mars in about 40 minutes. It crosses the entire width of our solar system from the Sun to Neptune in roughly 6 hours. You get one shot. There is no slowing down, no looping back, no course corrections once you're up to speed. Slowing down would require just as much energy as speeding up, and you simply cannot carry that kind of energy on a spacecraft that weighs a gram. The probe would streak past Proxima Centauri at 60,000 kilometers, giving you perhaps a few hours or at most a few days when it's close enough to capture meaningful images and measurements. And then it would be gone forever, racing into the blackness of interstellar space with no hope of retrieval or return, silently drifting for eternity. So while Breakthrough Starshot is a brilliant concept and grounded in real physics rather than science fiction, it remains highly theoretical. The necessary technology doesn't exist, and the engineering challenges are monumental. Even if we somehow built such a spacecraft tomorrow and launched it successfully, it would still take 20 years to arrive at Proxima Centauri and another 4 years for its data to reach Earth. That's a 24-year round trip for information, assuming everything works perfectly, something history has shown is never guaranteed in space exploration. And remember, this is just to reach our nearest stellar neighbor. With technology we can build today, using real rockets, real materials, real computers, the trip wouldn't take decades, it would take millennia. We'd need to build multi-generational starships, vast vessels capable of sustaining human life for thousands of years. The people who eventually arrived at Proxima Centauri would not be the ones who launched. They would be the distant descendants of those original travelers, separated by hundreds of generations. They would have lived their entire lives aboard a spacecraft they never chose, traveling toward a destination they had never seen except in stories passed down through centuries. And this brings us to one of the most profound consequences of the light year as a unit of distance. Distance and time become inseparable. When you look at the night sky, you're not seeing stars as they are, you're seeing them as they were. Light travels at a finite speed. It's incredibly fast, but not instantaneous. When light leaves a star and travels toward Earth, that journey takes time. And during that time, the universe continues to change. A star might brighten or dim. It might flare. It might evolve. It might explode. By the time that light reaches your eyes, the star you're looking at might be different from how it appears, or it might no longer exist at all. Take Sirius, the brightest star in the night sky. Sirius is 8.6 light years away. That means when you look at Sirius tonight, you're seeing light that left the star 8.6 years ago. You're seeing Sirius as it was when you were 8.6 years younger. If you're 20, you're seeing Sirius as it appeared when you were about 11. If you're 40, you're seeing it as it was when you were in your early 30s. The Sirius you see tonight is not Sirius as it exists at this exact moment. Fortunately, Sirius is a stable main sequence star. It isn't going to change drastically over the span of a few years or even a few decades. In 6 years, Sirius doesn't age in any noticeable way. Stars evolve over millions or billions of years, not over decades. From a human perspective, they are almost frozen in time. But the principle is what matters. You're not seeing Sirius as it is, you're seeing it as it was. Every time you look at a star, you're looking backward in time. Consider Vega, another bright star, about 25 light years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left the star in the year you were born. When that light began its journey toward Earth, you didn't exist yet. You were still years away from taking your first breath. Your parents perhaps looked up at Vega decades ago and saw light that left the star their generation earlier. The Vega you see tonight is a younger Vega, showing you the star as it looked a quarter century ago, not as it is right now. Now think about Betelgeuse, the red supergiant in Orion, one of the most famous stars in the night sky. Betelgeuse is about 550 light years away. The light you see from Betelgeuse tonight began its journey in the year 1474 during the height of the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was only 22 years old and Michelangelo hadn't even been born yet. In 1474, the Byzantine Empire had fallen to the Ottomans just 2 decades before. The printing press was a recent invention, barely 20 years old. Europe was still emerging from the Middle Ages. The modern world as we know it did not exist. And yet the light you see tonight from Betelgeuse set out during that era, crossing 550 years of darkness, traveling relentlessly toward Earth, arriving now in your eyes, this very moment. Betelgeuse is especially fascinating because it is a massive star nearing the end of its life. Stars like Betelgeuse live fast and die young, They burn through their fuel far more rapidly than smaller stars like our Sun. At some point in the relatively near future, astronomically speaking, within the next 100,000 years, Betelgeuse will explode as a supernova. When it does, it will briefly shine as bright as the full moon visible even during daylight. It will be one of the most spectacular astronomical events humans have ever witnessed. But here's the astonishing part: Betelgeuse might have already exploded. The explosion could have happened centuries ago, perhaps in 1600 or 1700 or 1800, but we wouldn't know. We cannot know. The light from that explosion would still be traveling toward us, taking 550 years to cross the gulf between Betelgeuse and Earth. The star you see tonight might no longer exist as it appears. You might be looking at the ghost of a star long gone, its final moments still racing through the cosmos toward us, not yet arrived. That is the power of the light year. It is not just a unit of distance, it is a window through time. And the farther we look into the universe, the farther back in time we see. The stars closest to us show us the last few years or decades of cosmic history. But as you move beyond them to stars hundreds, thousands, or millions of light years away, you begin to witness epochs that long predate human civilization. A galaxy a million light years away shows us what it looked like a million years ago. A galaxy 10 million light years away shows us the universe as it was when early humans hadn't even existed yet. A galaxy 100 million light years away reveals a cosmos from before the dinosaurs ever walked the earth. The deeper we peer into space, the deeper we peer into time. This is why telescopes are often described not just as instruments of observation, but as time machines. They don't let us travel backward in time. They simply allow us to see backward, to witness ancient light still streaming across unimaginable distances. Every photograph from the James Webb Space Telescope is a portrait of the past. Some of those images show galaxies from billions of years ago, galaxies forming when the universe was young, still glowing with the heat of creation. And that's another astonishing truth about light years. Once you understand them, you start to realize that the night sky is not a picture of the universe as it is. It is a mosaic of different eras stitched together across vast distances. Some stars are showing us their present, others are showing us their medieval past. Others are showing us what the universe looked like when humans did not yet exist. The sky above you is not a single moment in time. It is a timeline spread out across the blackness of space. Understanding this doesn't make the universe feel smaller. It makes it feel deeper, richer, more intricate. Each point of light becomes more than a star. It becomes a message, a fragment of history, a snapshot from a time long gone. And all of this, every bit of it, is encoded in that simple, beautiful, deceptively ordinary word, light year. Sirius B is completely different. It's a white dwarf, the dense compressed remnant of a star that has exhausted its nuclear fuel and collapsed under its own gravity. White dwarfs are extraordinary objects. Stellar corpses still glowing with residual heat, no longer fusing hydrogen, but still emitting light. Despite being roughly the size of Earth, A white dwarf has the mass of a star. Sirius B contains nearly the mass of our Sun, packed into a sphere about as wide as our planet. That makes it unimaginably dense. A single teaspoon of material from Sirius B would weigh about 5 tons on Earth. Sirius A and Sirius B orbit each other every 50 years, locked together by gravity, tracing elegant elliptical paths around their shared center of mass, a celestial dance continuing long after the original massive star collapsed into the white dwarf we observe today. Now, zoom out. The Milky Way, our home galaxy, is a vast spiral system containing somewhere between 100 billion and 400 billion stars. That number has a wide range because counting stars from inside a galaxy is incredibly difficult. We're embedded inside it, trying to count trees while standing deep inside a forest. Dust clouds obscure large portions of our view. Dim stars are nearly invisible across great distances. And the sheer scale of the Milky Way makes global measurements challenging. But our best estimates suggest around 200 to 300 billion stars, with our Sun being just one of them. An ordinary yellow dwarf of average size and brightness. It isn't unusually hot. It isn't especially luminous. It isn't particularly large or small. The Sun is ordinary, a typical star one among hundreds of billions, and it's located within one of the Milky Way's spiral arms, about 26,000 light years from the galactic center. 26,000 light years. The light we receive from the galactic center, if we could see through the dust that hides it, left 26,000 years ago. When that light began its journey toward us, humans were living as Stone Age hunter-gatherers. There were no farms, no cities, no writing, no civilization. People lived in nomadic bands, following animals, gathering wild plants, crafting tools from stone. Writing wouldn't appear for another 21,000 years. Everything we associate with human civilization, from the first agriculture, the first cities, the first writing systems, to all ancient cultures, all histories, all scientific discoveries, all technological revolutions, has unfolded during the time that light was traveling from the galactic center to Earth. And that ancient light, which began its journey when humans still roamed the plains of Africa, arrives in our telescopes tonight. The Milky Way is roughly 100,000 light years across from one side of the spiral disk to the other. If you could travel at the speed of light, which you can't, it would take 100,000 years to traverse the galaxy. 100,000 years. Modern humans, Homo sapiens, have existed for about 300,000 years as a species, so if the very first humans had set off across the galaxy, traveling at light speed, they'd only be 1/3 of the way across today. Meanwhile, the Sun itself is not motionless. It orbits the galactic center at a speed of about 230 kilometers. That sounds fast, and it is fast. At that speed, you could cross the entire United States in about 3 minutes. You could circle the Earth in just under 3 minutes. But even at this astonishing velocity of 230 kilometers, the Sun still needs about 225 to 250 million years to complete a single orbit around the Milky Way. Think about that. The last time the sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared around 230 million years ago. Since then, dinosaurs rose to dominance, thrived for more than 160 million years, vanished in a mass extinction, and million years ago, mammals diversified, primates evolved, and eventually humans appeared. And throughout that entire unfolding of Earth's history, the Sun has completed only one galactic orbit, returning just now to roughly the same position it held when the dinosaurs first emerged. One of the most thrilling developments in modern astronomy has been the discovery of exoplanets, planets orbiting stars other than our Sun. Until 1992, we knew of only one planetary system, our own solar system. 8 planets, countless smaller objects, all orbiting the Sun. We strongly suspected other stars had planets, but we had no direct proof. That changed in 1992 when astronomers detected the first known planets orbiting a pulsar. Then, in 1995, they found the first exoplanet orbiting a normal sun like star. Since then, the discoveries have exploded. As of 2024, astronomers have confirmed more than 5,000 exoplanets, with thousands more awaiting verification. One of the most extraordinary discoveries is the TRAPPIST-1 system, about 40 light years away. It contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of these worlds lie in the star's habitable zone, where temperatures might allow liquid water to exist on the surface. Announced in 2017, this discovery was revolutionary because it proved that small red dwarf stars, the most common type of star in the galaxy, making up 70% of all stars, can host multiple rocky planets. This implies that rocky planets might be everywhere in the universe, far more common than we once imagined. The TRAPPIST-1 system is also remarkable for its compactness. All 7 planets orbit closer to their star than Mercury orbits our Sun. But because the star is cool and dim, 3 of those planets receive Earth-like amounts of energy. If you stood on one of these planets, you would see the neighboring worlds filling the sky, some appearing larger than Earth's moon. The planets are so tightly packed that travel between them would be far easier than travel between planets in our own solar system. But remember, when we observe the TRAPPIST-1 system today, we're not seeing it now. We're seeing it as it was 40 years ago in 1985. Light from those planets left back when personal computers were new, when the Berlin Wall still stood, when many technologies we take for granted today did not yet exist. That's the nature of cosmic distance. Every exoplanet we discover is also a glimpse into the past. If there's intelligent life on one of those planets, and if that life developed radio technology and began broadcasting signals into space, those signals would take 40 years to reach us. We would be receiving right now transmissions they sent out in 1985. And if we detected such a signal today and sent a reply, our message would take another 40 years to reach them. They would receive our answer in 2065. That's an 80-year round trip for a single exchange of information. You could ask a question and live your entire life without ever hearing the response. This is what communication means when distance is measured in light years. It's one of the most challenging, sobering consequences of cosmic scale, and it fundamentally changes how we imagine humanity's future among the stars. It also shapes our expectations for contact with alien civilizations. Radio waves travel at the speed of light. They are electromagnetic radiation, just like visible light, but with longer wavelengths. When we send radio signals into space, they expand outward in all directions at 300,000 kilometers. But even at the fastest possible speed allowed by physics communication across interstellar distances takes years, decades, or longer. Take Voyager 1, our most distant spacecraft. It's now about 24 light hours from Earth. That means there's a communication delay of 24 hours each way. When mission controllers send a command to Voyager, that command travels at light speed across 25 billion kilometers, finally reaching the spacecraft a day later. Any data Voyager returns takes another 24 hours to arrive on Earth. A simple two-way conversation takes roughly 48 hours. If something goes wrong, if a system fails, or an anomaly happens, Voyager must detect the issue and handle it autonomously. Earth cannot react in real time. By the time we learn of a problem, the moment has already passed. The spacecraft is on its own. By the time engineers on Earth become aware that there's a problem and send new commands to correct it, 2 full days have passed. In that time, the situation on board could have changed dramatically. The spacecraft might have already recovered, already failed, or already shifted into an entirely different condition. Consider New Horizons, the spacecraft that performed the historic flyby of Pluto in July 2015. During its closest approach, it was about 4.5 light hours from Earth. Every image, every measurement, every precious data packet collected during those fleeting hours had to be stored on board because nothing could be transmitted instantly. Only months later, after careful scheduling and slow, steady communication, did all that data finally arrive on Earth. Every command sequence had to be written weeks or months in advance. Mission controllers couldn't respond to what New Horizons was seeing in real time. They had to plan perfectly, anticipate everything, and trust the spacecraft to make the right decisions autonomously. Spacecraft that far away must essentially think for themselves. Now imagine trying to communicate with a human colony on a planet orbiting Proxima Centauri 4.24 light years away. You send a simple message. How are things going? How are the crops? Do you need anything? Your message travels at light speed for 4.24 years, 4 years, 2 months, and about 20 days later it arrives. If they reply immediately, their answer takes another 4.24 years to reach you. That's more than 8 years for a single exchange. You could ask about their most recent harvest and receive an answer about crops that were eaten or spoiled 4 years ago. You could ask how a sick person is doing and receive word of their death years after it happened. You could offer advice, guidance, or assistance, but by the time your message reached them, the situation might already be resolved, or it might have worsened beyond recognition. Any real time communication, the kind of instant back and forth we take for granted, becomes impossible across such distances. Conversations would be achingly slow, arguments would span decades. Diplomacy between Earth and a Proxima colony could take a century to settle a single dispute with each side waiting years just to hear the next sentence of the conversation. This isn't merely inconvenient, it has profound implications for the very structure of society and governance. A colony 4 light years away cannot be governed from Earth in any meaningful sense. Laws, directives, or policies sent from Earth would arrive years out of date. The political landscape on Earth could transform entirely between the sending and receiving of a message. By the time a colony received orders, those orders might already be irrelevant, overturned, or issued by a government that no longer exists. Such a colony would need complete autonomy, able to make its own decisions about resource management, conflict resolution, emergency responses, scientific priorities, and all aspects of daily life. Because waiting years for approval or guidance on every decision would be impossible, any colony that far away would inevitably develop its own customs, its own problem solving methods, its own cultural identity. Earth and its distant settlement would remain connected only by messages from the past letters arriving out of sync with the present reflections of a world that no longer exists by the time they are received. Over generations, the two societies would drift apart so dramatically that they might barely recognize one another. They would share a common origin, a shared history, up to the moment of separation, but from that point onward, they would diverge, evolving in isolation, like species separated on distant islands. And the farther away a settlement is, the more extreme this separation becomes. A colony 10 light years away would have a 20-year communication delay. A message you send today might reach your children when they are adults or when they have children of their own. Their reply would return when your grandchildren are grown, when you are elderly, or possibly no longer alive. You would exchange messages across decades, like letters from different eras, able to share news, but unable to share life. A civilization 100 light years away would have a 200-year round trip delay. You could send a message into the void, but neither you nor your children, nor your grandchildren, nor even your great grandchildren would see the reply. Only your distant descendants, people living in a world you cannot imagine, might someday receive an answer. The conversation would span generations. Each generation would write to strangers they will never meet, receiving messages from people long dead. Communication becomes a kind of time capsule, voices echoing back and forth across centuries. And yet, something even stranger happens if you travel at speeds close to the speed of light. This is Einstein's time dilation, one of the most extraordinary and well confirmed results in all of physics. It isn't speculation, it isn't a thought experiment. It's real, measured, tested, and as reliable as gravity or magnetism. As you approach light speed, time slows down for you compared to someone standing still. The faster you go, the more dramatic the effect becomes. And this isn't just a clock ticking slower, it's you experiencing time differently. Your heartbeat, your thoughts, your aging, your metabolism. All of it runs more slowly compared to the outside universe. Yet, from your own perspective, inside the spacecraft, everything feels normal. Your time flows naturally. It's everyone else whose clocks seem to race forward. Imagine a spacecraft that somehow reaches 99.9% of the speed of light. You board this ship and travel to a star 10 light years away, then turn around and come back. From Earth's perspective, the journey takes about 20 years, roughly 10.1 years each way, at 99.9% light speed. Anyone watching from Earth would see the trip take 2 decades. But you, because of time dilation, you would age far less. At 99.9% light speed, time passes about 22 times slower for you than for those on Earth. So, while 20 years pass on Earth, you experience less than 1 year, about 11 months of subjective time. You would step off the spacecraft having aged less than a year, while everyone you know has aged 2 decades. Your younger sibling might now be older than you. Your children, if you had any, might have grown into adults older than you appear. You would have traveled into their future. If you travel even faster, say 99.99% of light speed, the effect becomes more extreme. You could travel to a star 100 light years away and back. From Earth's viewpoint, the trip takes over 200 years. But from your perspective, due to the intensifying time dilation, the entire journey might last only a few years. You would live through those years aboard the spacecraft experiencing only a small slice of time. But when you return to Earth, more than 200 years would have passed. Everyone you knew would be long dead. Entire generations would have lived and died in your absence. The world would be unrecognizable. Political systems would have shifted. Technologies would have advanced far beyond anything you remember. Languages might have evolved into forms you barely understand. You wouldn't just be returning home, you'd be arriving in a future Earth as foreign to you as if you had stepped out of a time machine. Now let's zoom out even further. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old, and for all that time, light has been traveling toward us. But the observable universe isn't 13.8 billion light years across, it's much larger. That's because while light was traveling, space itself was expanding, stretching the distances between galaxies. As a result, the observable universe extends about 46.5 billion light years in radius, making it roughly 93 billion light years across. That's the edge of what we can possibly see, the limit imposed not by our telescopes, but by the laws of physics. Beyond that cosmic horizon, light simply hasn't had enough time to reach us, and due to the expansion of space, much of it never will. Within this observable universe exist an estimated 2 trillion galaxies. Each galaxy contains billions or even trillions of stars. If you multiply those numbers, the total number of stars in the observable universe is around 200 billion trillion, a 2 followed by 23 zeros. And because we've learned that most stars host at least one planet, the number of planets likely matches or exceeds that number. That means the universe is filled with worlds. More worlds than we could ever count. More worlds than we could ever visit, even with unimaginable technology and limitless time. On the largest scales, the universe has structure. Galaxies aren't sprinkled randomly like grains of sand. Instead, they gather into clusters held together by gravity. These clusters assemble into even larger structures called superclusters, and those superclusters weave together into enormous cosmic filaments, threads of galaxies stretching hundreds of millions of light years across space. Between these filaments lie enormous voids regions, almost completely empty, stretching across similar vast distances. The universe is not uniform, but patterned like a cosmic web spanning unfathomable distances. And overlaying all of this is one of the most important facts in cosmology. The universe is expanding. Space itself is stretching, carrying galaxies with it. This isn't galaxies flying apart through space. This is space growing between them, like raisins embedded in expanding bread dough. For nearby objects, this expansion is imperceptible because stronger forces dominate. Gravity binds the Earth and Moon together. Gravity holds the solar system intact. Gravity keeps the Milky Way's stars orbiting the galactic center. Within galaxies, within solar systems, within planetary orbits, space is not expanding in any meaningful way. But on larger scales between galaxies, between clusters, the expansion is relentless and accelerating. But on larger scales between galaxies, and especially between galaxy clusters separated by hundreds of millions or even billions of light years, the expansion of space becomes significant and eventually dominant. Distant galaxies are receding from us, not because they're flying through space at incredible speeds, but because space itself is stretching between us and them. The farther a galaxy is, the faster it appears to recede. That simple relationship distance determines recession speed is a direct consequence of expanding space. And here's the strange part. For galaxies far enough away, the expansion of space between us and them exceeds the speed of light. This doesn't violate any physical laws because the galaxies aren't moving faster than light through space. They're essentially stationary in their local regions. It's the fabric of space doing the stretching, like being on a treadmill moving backward faster than you can walk forward. You're walking at your normal pace, but you still drift away from your starting point because the treadmill's motion dominates. This leads to a profound consequence. There are regions of the universe that are receding from us so quickly because space is expanding so fast that light from those regions will never reach us. Ever. Not in a billion years, not in a trillion years, not in any amount of time. They lie beyond a cosmic horizon, not a horizon caused by distance, but by destiny. Light trying to travel toward us is forever swept backward by the expansion of space. That light will never bridge the gap. Those regions of the universe are permanently, irreversibly inaccessible to us, and this horizon grows with time. Every day, more galaxies cross beyond it. The observable universe shrinks not in size, but in what it can ever meaningfully interact with. We occupy one tiny island in an ocean whose distant shores are receding beyond reach. Given the mind boggling number of stars and planets in the universe, given that the universe is 8 billion years old, given that life on Earth emerged relatively quickly once conditions allowed it, it seems almost inevitable that life should exist elsewhere. perhaps intelligent life, perhaps technological civilizations, perhaps beings that have built machines, cities, networks, communication systems just as we have. And yet we detect nothing. No radio signals, no engineered electromagnetic noise, no bursts of laser communication, no artificial megastructures blotting out starlight, no astroengineering on galactic scales, nothing but silence. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" And the answer, at least part of it, might lie in the very concept we've been exploring all along. The light year isn't just a measure of distance, it's a measure of separation, a barrier, a filter. The universe may be full of life, but the distances between stars, between civilizations, may be so impossibly vast, so dominated by the limitations of light speed and the expansion of space, that no species can easily bridge them. Even if intelligent life is common, communication may be nearly impossible. Travel may be effectively impossible. Civilizations may be trapped in isolated pockets of space-time, unable to reach or hear one another across the cosmic gulf. The universe isn't empty, it's just too big. Our radio signals, our early television broadcasts, radar pulses, military transmissions have been leaking into space for roughly a century. These signals travel at the speed of light, expanding outward in an ever growing sphere centered on Earth. Today, that sphere has reached a radius of about 100 light years. 100 light years sounds immense. By human standards, it is. But compared to the scale of the Milky Way, a galaxy 100,000 light years across our reach is almost nothing. Our electromagnetic footprint is a tiny bubble, a microscopic ripple in an ocean of stars. We've barely whispered into our immediate cosmic neighborhood, and already that whisper is fading. Because as these signals travel outward, they weaken dramatically. The farther they go, the more thinly they spread, diluted across a sphere that grows larger every second. By the time our old TV broadcasts reach a star, even a few dozen light years away, they are so faint they are nearly indistinguishable from the natural radio noise of space itself. For an alien civilization to detect us, they would need enormous, exquisitely sensitive radio telescopes, pointed precisely at Earth, tuned to the right frequency, at exactly the right moment. Otherwise, our presence dissolves into the cosmic background unnoticed. So, what does all of this mean for us, for ordinary human life? Most of the time, light years don't matter when you're choosing breakfast or deciding whether to carry an umbrella. The distances between stars don't affect your commute, your errands, your chores, or your plans. But there is value, real value, in occasionally stepping back and contemplating the immense scales of the universe. Because when you understand these distances even just a little, it changes the way you see the world. You begin to grasp that Earth is a tiny planet orbiting a perfectly ordinary star, that the nearest other star is more than 4 light years away, that our galaxy contains hundreds of billions of stars, that the observable universe contains trillions of galaxies. And suddenly, your entire life, your memories, your hopes, your joys, your worries, are seen against the backdrop of a cosmos so vast it defies comprehension. Your problems still matter. They matter deeply because they matter to you. Pain is real, stress is real, love, fear, uncertainty. These are the textures of being human. But when life feels overwhelming, when anxiety builds, when frustration rises, when the future feels unclear, it can help to remember that the universe is vast, ancient, and unfolding on scales far beyond anything we face day to day. Your struggles are not meaningless, they are simply small in the cosmic sense, contained, temporary, manageable. You exist on a quiet blue world, orbiting an ordinary star in a galaxy full of billions of suns. And for this brief moment in time, you are here breathing, thinking, feeling, one consciousness among countless possibilities in a universe that stretches beyond imagination. There's also something deeply beautiful about understanding light years. When you look up at the night sky, you're not simply seeing points of light scattered across the darkness. You're seeing suns, true stars, lying light years away. You're seeing photons that have been traveling through the void for years, decades, centuries, crossing unimaginable distances just to arrive in your eyes at this precise moment. There is something profoundly connecting in that. You, a being made of atoms forged in ancient stars, are looking back at other stars, recognizing your place in the cosmic story. Every star has a life. Some are young, still forming inside, collapsing clouds of gas and dust, stellar nurseries where gravity sculpts new suns. Some are middle aged, like our sun, quietly fusing hydrogen into helium, stable, unhurried, living out billions of years in balance. Some are old, nearing the end, swollen, unstable, or exhausted. They will become white dwarfs, glowing faintly for trillions of years, or they will explode as supernovae scattering their atoms into space, where they will be recycled into new stars, new planets, perhaps new life. And in every one of these stars is separated from every other by light years. Distances so large that even light requires years to cross them. The universe is a vast, sparse ocean dotted with tiny islands of fire. Yet those islands are connected by light, by gravity, and by their shared ancestry. Every atom in your body, carbon, oxygen, iron, was forged inside a star long before the sun existed. You are literally stardust reassembled by cosmic processes billions of years old. As our technology evolves, our ability to measure these distances becomes ever more precise. The Gaia spacecraft is mapping the Milky Way in exquisite detail, measuring the positions and distances of over a billion stars, creating the most accurate 3D atlas of our galaxy ever attempted. New telescopes look farther still. The James Webb Space Telescope already detects galaxies more than 13 billion light years away, light that began its journey when the universe was young. Future observatories will push even closer to the Big Bang. We're also identifying more exoplanets every year, over 5,000 confirmed so far, some dozens, some hundreds of light years away. We're building a map not only of stars, but of worlds. And someday, if our engineering advances enough, we may send robotic probes to the nearest stars. Breakthrough Starshot imagines ultralight spacecraft pushed by lasers to 20% light speed reaching Proxima Centauri in just over 20 years and sending back data 4 years after that. Yet, even this ambitious concept doesn't escape the fundamental truth. Light years impose a barrier we cannot cross faster than light itself. Unless physics changes, light years will always shape what is possible. They are not an inconvenience to overcome. They are the architecture of the universe. Understanding light years transforms how we see ourselves, our future, and our place in the cosmos. For most of human history, the universe was small. Ancient cultures imagined the stars attached to a celestial dome just beyond the moon. The cosmos was a finite sphere, reachable if only one could climb high enough. Even after we realized the stars were suns, their true distances were unknowable, beyond the precision of our instruments, and beyond the scale of our imaginations. Numbers like millions or billions of kilometers were abstract, unanchored. Only in the early 20th century did we finally begin to map the stars with accuracy. In 1918, Harlow Shapley shocked the astronomical world by demonstrating that the Milky Way was roughly 100,000 light years across a structure far vaster than anyone believed. And then, in 1929, Edwin Hubble showed that the spiral nebulae were not clouds within our galaxy at all, but entire other galaxies millions of light years away. With that discovery, the universe expanded again, exploding in size by orders of magnitude. What we once thought was the entire cosmos became just one galaxy among countless others. We went from believing the Milky Way was the entire universe to realizing it was merely one galaxy among potentially billions. Today, we know the observable universe is roughly 93 billion light years across and contains an estimated 2 trillion galaxies. It's a number so huge it becomes almost meaningless, yet it describes a real physical space surrounding us in every direction. If your eyes could see far enough, if nothing blocked your view, you would see galaxies stretching outward in all directions, receding into the distance like cosmic lanterns. More and more sphere of them fainter and farther until finally you reached the edge of the observable universe, the boundary where light simply hasn't had enough time to reach us yet. This understanding reshapes our perspective in profound ways. We are not at the center of the universe. We are not cosmically privileged. We live on a typical planet, orbiting a typical star, inside a typical galaxy, in a typical part of the cosmic web. If you were magically transported to another galaxy billions of light years away, the universe would look broadly the same galaxies in every direction stretching toward the cosmic horizon. The universe is uniform on the largest scales, offering no special favoritism to Earth or to us. And that is both humbling and empowering. Humbling because it shows how small we are. Everything humans have ever done, every painting, every war, every poem, every invention, every heartbreak, every triumph has unfolded on a single tiny world orbiting an ordinary star. In cosmic terms, our entire history may as well be the flicker of a firefly in a vast, endless night. From the universe's perspective, we barely exist. But it's also empowering because somehow, against all odds, we figured this out. We measured these distances. We discovered our place in the cosmos. We built telescopes, developed mathematics, launched spacecraft, and pieced together the story of a universe billions of years old and billions of light years across. We are small, yes, but we are capable. We are stardust that became conscious enough to understand the stars. Understanding light years forces us to confront the reality that interstellar exploration may be far more challenging than our science fiction fantasies suggest. The distances involved are so enormous, they may represent a true physical barrier's limits that no amount of engineering brilliance can fully overcome. Consider what it would take to send humans to another star. Proxima Centauri, the nearest one, is 4.24 light years away. With current technology, the fastest spacecraft ever built, Parker Solar Probe, moves at about 192 kilometers at its peak. Even at that record breaking speed, it would take about 800 years to reach Proxima Centauri. That's longer than all of recorded human history. If you had launched such a mission when humans first invented writing, the spacecraft still wouldn't have arrived today. To make interstellar travel even remotely practical, we would need to travel much faster. Even at 10% of the speed of light, a velocity far beyond anything we can currently build, requiring revolutionary propulsion physics, it would still take over 42 years just to reach Proxima Centauri. 42 years, longer than a typical career, longer than the duration between your graduation and your retirement. And that's just to reach the nearest star, our next door neighbor in cosmic terms. Most stars are vastly farther away than Proxima Centauri, and the engineering challenges mount rapidly as distances increase. To accelerate a spacecraft to even a fraction of light speed requires staggering amounts of energy far beyond anything humanity currently produces. You'd need shielding to protect the crew from cosmic radiation. You'd need life support systems that can operate reliably for decades. And you'd need to confront the psychological weight of spending an entire lifetime confined to a small spacecraft, leaving Earth behind forever, traveling through darkness toward a destination you may never live to see. This is why multi generational starships have been proposed massive self sustaining habitats carrying hundreds or thousands of people living and dying over centuries as the ship drifts through interstellar space. The people who finally reach another star would be the distant descendants of those who launched the mission. They would have been born aboard the ship, grown up aboard the ship, and their entire understanding of home would be the ship itself. The destination, another star, would be more myth than memory, a story passed down through generations like a cosmic legend. In effect, a multi generational ship would be a small, isolated civilization evolving its own culture values, languages, and identities during the long voyage. But even this concept faces extraordinary challenges. How do you maintain a closed ecosystem for centuries without failure? How do you prevent genetic bottlenecks and inbreeding in a relatively small population? How do you ensure that the descendants of the original crew still want to complete the mission? What if several generations in they decide to turn back or to go somewhere else entirely? What if disaster strikes a system, failure, a fire, a disease? There would be no rescue, no help, no second chance. They would be light years away from assistance. Suspended animation has been proposed as a solution, cryogenic freezing, placing the crew into a deep, dreamless sleep for decades or centuries, waking them only upon arrival. This would eliminate many logistical and psychological challenges. But at present, we have no technology capable of freezing and reviving a human being intact. Ice crystals damage cells. The brain is fragile. Long term memory might not survive. We don't know if cryogenic preservation is scientifically possible, and it may turn out to be fundamentally unworkable. The truth is, stark interstellar travel with living human passengers may simply be impractical within the laws of physics as we understand them. The light year is not just a measurement, it is a boundary, a constraint, a constant reminder that the universe is enormous and that the speed of light is an unbreakable limit. We may be confined to our solar system for a very long time, perhaps forever. That doesn't mean we can't explore the stars with robotic probes, tiny spacecraft that can survive centuries of travel. But human journeys to other stars may remain for the foreseeable future within the realm of imagination and science fiction. And the light year also shapes something equally profound: how we think about the possibility of alien civilizations, whether they exist, whether they see us, and whether we could ever communicate across such astonishing distances. If intelligent life exists elsewhere in the universe, and many scientists believe it, likely given the staggering number of stars and planets, the sheer distances involved may render contact impossible, even if both civilizations endure for millions of years. Imagine a technologically advanced civilization orbiting a star 50 light years from Earth. They've invented radio technology and have been transmitting signals for a century, just as we have. Their signals are now washing through our region of space, but after traveling 50 light years, they are unimaginably faint, spread across a sphere billions of kilometers wide. Detecting them would require extraordinary luck. Our most sensitive radio telescopes would need to be pointed at the exact right place, tuned to the exact right frequency, at the exact right moment. The odds of this happening by chance are microscopic, and even if we did detect such a signal, the next steps reveal the true scale of the challenge. The message we receive would be 50 years old, a snapshot of their world half a century in the past. If we responded immediately, our reply would take another 50 years to reach them. A single exchange of ideas would require a full century. You could ask a question today and die of old age before hearing the answer. Your grandchildren or great grandchildren might be the ones to receive the reply to something you asked. And that fundamentally transforms the very nature of communication. There can be no conversation in any normal sense, no dialogue, no discussion, no negotiation, no shared moment of discovery. Instead, it would resemble an exchange of encyclopedias. Each civilization might decide to transmit everything they know: science, history, mathematics, art, in hopes that a century later someone receives it and responds in kind. It becomes less communication and more archaeology studying the preserved records of a civilization as they existed decades or centuries before the message arrived. And this assumes the best case scenario that both civilizations remain stable, technologically capable, and interested in communication long enough for the exchange to occur. Humanity has broadcast radio signals for only about 100 years. We have no idea whether we'll still be transmitting a century from now, let alone several centuries. Civilizations may rise and fall on timescales shorter than the light travel time between stars. We might detect a signal from a society that vanished long before we hear it, a radio echo from a world that no longer exists. There's an even more unsettling possibility. The universe may be full of civilizations, yet all of them so widely separated that none ever make contact. If the average distance between intelligent species is thousands of light years, then meaningful communication becomes nearly impossible. Their signals fade into background noise. Their attempts at contact dissipate long before being noticed, and the time delay becomes so immense that exchanging even a single message becomes futile. Each civilization could live out its entire span, rise, flourish, explore, ponder the cosmos, ask whether it is alone, and then fade away, never knowing that others existed. One of the deepest implications of truly understanding light years is this quiet, sobering realization: we may be profoundly, permanently isolated. Not because the universe is empty, but because it is enormous. The distances between stars are so vast that meaningful contact or travel might be forever out of reach. Even in a galaxy that could host millions of civilizations, the average separation might still be measured in thousands of light years, rendering communication little more than a poetic gesture across the void. At those distances, messages become whispers swallowed by time, and civilizations remain alone, cosmic islands separated not by oceans, but by light itself. By the time you receive a message from a distant civilization, and by the time you respond, thousands of years may have passed. The beings who sent the original transmission might no longer exist. Their planet could have been shattered by an asteroid. Their civilization might have collapsed in war or disease. Their star might have changed, flared, or evolved in a way that made their world uninhabitable. You might be sending a message to ghosts. This paints a picture of a universe that could be full of life, perhaps even rich with intelligent civilizations, yet each one isolated by distances so immense that meaningful contact is effectively impossible. Each civilization grows alone, wonders, alone discovers alone, and eventually fades alone, never knowing whether the universe beyond its sky was silent or simply unreachable. There is a quiet melancholy in this vision. We are social creatures. Connection is woven into our biology. We build communities. We share knowledge. We rely on one another to give meaning to our existence. The idea that humanity might be cosmically alone or surrounded by others we can never reach is profoundly isolating. But there is also something undeniably beautiful in this solitude. If we are alone or alone for all practical purposes, then every civilization that arises is unique beyond measure. It means that we right now are the universe becoming aware of itself in this tiny region of space. The thoughts we think, the music we compose, the questions we ask, the love we feel, all of it is singular. All of it is unrepeatable. We may not be one voice among millions. We may be the voice of this corner of the cosmos. That makes what we do matter more, not less. Every act of kindness, every discovery, every creative spark, every moment of joy or curiosity, each one is precious precisely because it might not be happening anywhere else for dozens or hundreds of light years in any direction. We may be small, fragile, temporary, but we are also rare. We are irreplaceable. We are the lone flicker of consciousness in a vast expanse of darkness. Tonight, we've explored the light year from every angle, what it is, how it's measured, what kinds of distances it represents, and how deeply it shapes our understanding of the universe and our place within it. We've traveled together from the familiar scales of Earth kilometers, days, hours, to the almost unfathomable scales of stars and galaxies. A light year is 9.46 trillion kilometers, the distance light travels in a single year at 300,000 kilometers. Astronomers use it because kilometers and every human sized unit of measurement simply break down at cosmic scales. Light years are not just convenient, they are essential. They are the language of the universe. When you're measuring distances to stars and galaxies, you need a unit vast enough to make the numbers manageable, yet grounded in something physical and measurable. That is why we use the light year. The nearest star to our Sun, Proxima Centauri, lies 4.24 light years away. That is our closest stellar neighbor, and even so, with current technology, it would take thousands of years to reach it. Our own galaxy, the Milky Way, spans roughly 100,000 light years from edge to edge. Even if you could travel at the speed of light, a speed no object with mass can ever attain, it would take you 100,000 years to cross it. And the observable universe. It stretches an astonishing 93 billion light years across and contains an estimated 2 trillion galaxies, each one home to billions or trillions of stars. When you gaze at the night sky, you're not seeing stars as they are now. You're seeing them as they were when their light began its journey. Sirius 86 light years away appears to you as it was 8.6 years ago. Betelgeuse, roughly 550 light years distant, appears as it was during the Renaissance, more than 5 centuries before your own lifetime. This is what makes the light year so profound. It links distance and time, revealing that the two are inseparable aspects of space-time. The universe does not distinguish between where and when in the way our minds do. Every star you see is both a place and a moment in the past. And the speed of light, 300,000 kilometers, is not just fast. It is a fundamental limit, a boundary built into the fabric of space-time. Nothing with mass can reach it. Nothing can exceed it. This means that distances measured in light years represent real, physical barriers to travel and communication. Even if you could somehow ride a beam of light, you'd still need years to reach nearby stars, thousands or millions of years to reach distant galaxies. And because space-time itself is expanding and the expansion is accelerating due to the mysterious influence of dark energy, many galaxies are drifting away faster than their light can ever reach us. Billions of years from now, as expansion continues, the universe will appear more empty. Galaxies now visible will slip beyond our cosmic horizon, forever unreachable. Yet, despite these immense distances and the limits imposed by physics, humanity has learned an extraordinary amount about the universe. We've mapped billions of stars with exquisite precision. We've discovered thousands of exoplanets orbiting other suns, some potentially habitable. We've observed galaxies billions of light years away, capturing light that left them shortly after the Big Bang. And all of this has been possible because of one tool, the light year, our measuring stick for the cosmos. It lets us map the universe, trace its evolution, and understand our place within it. So let's end where we began. A light year is the distance light travels in a single year, 946 trillion kilometers, a number almost beyond comprehension, yet a number that gives us a way to grasp the scale of the universe, a number so large it challenges our ability to comprehend it, a distance so vast it makes our entire planet feel infinitesimally small in comparison. But you don't need to intuitively grasp the full scale of a light year to appreciate what it represents. You only need to understand that the universe is far larger than anything our senses evolved to perceive. You can appreciate that the light reaching your eyes tonight has been traveling patiently, relentlessly for years, decades, centuries, sometimes millennia. You can appreciate that we are living in an unremarkable corner of an extraordinary cosmos on a small world orbiting an ordinary star in a galaxy that is merely one among trillions. There is something profoundly humbling about understanding light years. It reminds us how small we are in the grand architecture of the universe, how brief our individual lives are compared to cosmic time, how isolated we truly are, separated even from our nearest stellar neighbors by distances that would take millennia to cross with any technology we've ever built. It puts our worries and stresses into perspective. From a cosmic viewpoint, the problems that consume us each day, arguments, frustrations, anxieties, are fleeting, local, temporary. They rise and fall within the blink of an eye compared to the slow, grand unfolding of the cosmos. But there is also something empowering in this knowledge. We figured this out. Small creatures living on a tiny planet, orbiting a nondescript star. We measured these distances. We unraveled the structure of space and time. We built telescopes capable of catching photons that have traveled billions of years. We constructed mathematical frameworks that allow us to comprehend realities far beyond our physical intuition. We may be confined to one small world for now, but we are remarkably capable. We are conscious beings who can understand the universe that made us. We can look at the night sky and not just see dots of light, but know what they are. We can contemplate scales measured in trillions of kilometers and ages measured in billions of years. From a cosmic perspective, you are insignificant. Your life is a brief flicker, perhaps 80 or 90 years, compared to a universe 13.8 billion years old and destined to continue for trillions more. You live on a tiny world orbiting an unremarkable star in a galaxy no different from countless others. And yet, you are also remarkable. You are made of atoms forged in ancient stars, stars that lived and died billions of years before the sun existed. Their ashes drifted through space, forming new stars and planets, eventually becoming the molecules that make up your body. You are literally stardust shaped by cosmic forces older than history. You are a way for the universe to understand itself, to look inward, to look outward, to feel wonder, to ask questions no other creature on earth has ever asked. So the next time you gaze at the night sky, remember what you learned tonight. Those points of light shimmering against the darkness are not just lights. They are suns, distant massive spheres of fusion. Each one may host its own planets, its own moons, its own stories, and they are light years away so far that the photons entering your eyes right now have been traveling for years or centuries. Some of that light began its journey long before you were born. Some began before your grandparents were born. And yet here it is touching you, connecting you to distant suns across the void. You are small in a universe vast beyond imagining, but you are here, and you can understand, at least conceptually, what a light year truly is. You can grasp that the universe is measured in distances that dwarf everything in human experience, and that ability to look up to wonder, to comprehend even a fraction of the cosmos, is one of the most extraordinary things about being human. And that understanding, that ability to comprehend your place in the cosmos, is extraordinary. It's what makes us human. It's what separates us from every other form of life on Earth. We can look up and know what we're seeing. We can contemplate infinity and our own smallness at the same time. We can feel humbled and empowered by the very same knowledge. And perhaps that is the most important thing to take away from understanding light years, not just the technical definition, not just the mathematics of 9.46 trillion kilometers, but what it means for us as a species, for our future, for our identity, for our place in the cosmos. We stand at a unique moment in history. We are the first generation of humans who truly understand the scale of the universe. Our ancestors looked up at the same stars and asked the same questions, but they had no tools, no physics, no instruments to measure the answers. They didn't know the stars were distant suns. They didn't know those suns were light years away. They couldn't comprehend the immense distances separating us from everything else in the universe. But we can. We have measured these distances. We've calculated them with extraordinary precision. We know Proxima Centauri is 4.24 light years away. We know the Andromeda Galaxy is 2.5 million light years distant. We know the observable universe spans 93 billion light years across. These are not guesses. They are not poetic metaphors. They are measurements carefully gathered, rigorously verified, backed by a century of observation and physics. And knowledge like this changes us. It has to. When you understand that even the nearest star would take thousands of years to reach with today's technology, when you grasp that the light from distant galaxies began its journey billions of years ago, when you realize that we may be fundamentally isolated by the sheer scale of the cosmos, your entire perspective shifts. Our differences begin to feel smaller. The arguments, the borders, the conflicts, all of them unfold on a single tiny planet floating in an incomprehensibly vast cosmos. We're all together on this fragile world, separated from our nearest stellar neighbors by distances measured in light years. From that vantage point, the things that divide us shrink. The things we share grow. It also makes our existence feel more precious. If we're alone, or effectively alone, because no one else can reach across the light year gulf, then what happens here matters even more. We might be the only consciousness for dozens, hundreds, perhaps thousands of light years in every direction, the only beings capable of contemplating the universe, the only minds able to turn stardust into thought, to turn curiosity into science, to turn existence into meaning. That is a profound responsibility. It means we must care for this planet, this small, fragile island of life, adrift in the vast cosmic ocean. It means we have a responsibility to protect the knowledge we've gathered, the understanding we've worked so long to build. It means we have to think in long horizons, not just in years or decades, but in centuries, in millennia, imagining the distant future of humanity beneath other suns. Because the light year is more than a measurement. It's a reminder of where we stand in the universe. Tiny, yes, but not insignificant. Part of something unimaginably vast, yet also something rare and precious within that immensity. It reminds us that the stars are both impossibly far away and deeply connected to us through the light that crosses the darkness to reach our eyes. Every time you look up at the night sky, you are taking part in something ancient, something shared by every human who has ever lived. You are seeing across light years. You are looking backward in time. You are witnessing the universe revealing itself one photon at a time. And you are part of that universe made of the same atoms, shaped by the same laws of physics, held together by the same forces that bind galaxies, stars, and worlds. That is what a light year truly represents, not just distance, but connection, not just separation, but belonging, not just our smallness, but the quiet significance that exists within that smallness. Thank you for traveling through space and time with me. If this journey meant something to you, a like or a subscribe helps me continue creating these deep explorations of the cosmos. And remember, even though light years describe distances almost beyond imagination, they are also the very bridges that link us to the stars. Every time you lift your eyes to the night sky, you're reaching across those distances. You're seeing the universe, and the universe, vast, ancient, and breathtaking, is yours to explore. Good night, and may you never look at the stars the same way again.